Hello everyone, I'm preparing this video to serve for our quantum computing course for distance learning due to the new coronavirus going all over the world. So the whole video lecturing will be an interesting experience for me. Okay, so in our last lecture we talked about quantum teleportation and how we could transfer the state of a qubit and also the complementary process of this of teleportation, so-called the superdense coding. Today we will finally look at quantum algorithms. I must have also mentioned about the reason behind the advantage of quantum algorithms over the classical ones for certain problems. And the reason is it's really due to the fact that the tensor products of systems produce the multiplication of the dimension of the smaller subsystems rather than their summation. So when we take the tensor products, as the size of the system grows, the size of the vector space of the combined system grows exponentially. This is one reason why quantum algorithms outperform classical algorithms for certain problems. Not all, but certain problems. Okay, so today we will start with the most simplest quantum algorithm called Deutsch's algorithm. Deutsch's algorithm. Now this is perhaps the most simplest quantum algorithm in the literature. The problem is due to David Deutsch, and which he introduced in his 1985 paper. So the problem concerns a function from 0, 1 to 0, 1 is a function. Okay, so it's a binary function which takes either 0 or 1, and it maps to either 0 or 1. We say that, let's define this notion. Okay, so if f of 0 equals f of 1, then we say that f is a constant function. Okay. Otherwise, if f of 0 is not equal to f of 1, otherwise f is balanced. All right. Now the problem is, Deutsch's problem is, now given a function f from 0, 1 to 0, 1 as a black box, okay, now we're given a function f as an oracle, as a black box. We can evaluate the function f, but we cannot look inside the function, okay, it's forbidden. So we do not know how the mechanics of the function works. We're just allowed to evaluate f as an oracle, that is, as a black box. So the problem is to determine if the given function is if f is constant or balanced. Okay. All right, so let's think about this problem for a while. And let's think in terms of classical computers. Now, classical computers can solve Deutsch's problem by evaluating f on both inputs, actually, on 0 and 1. So we should first evaluate f on 0 and see what the output is. But we should also evaluate f on input 1 and then compare the outputs of the function and tell whether the function is constant or balanced. So we need at least two queries: classical algorithm can solve this problem in, well, actually at most, exactly 2 queries. Okay. Okay, so but with quantum computing, we will see that we can solve this problem using only 1 query. Only 1 query. Okay. So before going into the details, let's describe how we can define function f in terms of matrices. Now, classically defined, a function can be thought of as a black box, okay, having an input and an output, x, y. This is a classical representation of a function. And a 1-bit input and a 1-bit output function can be represented by a 2-by-2 matrix. Okay. For instance, if a function, if f was defined as something like, if f0 was 0 and f1 was 0. So if f was a constant function, then I could represent f by the matrix 1, 0, 1, 0, right? So it maps ket 0 to ket 0, and it maps ket 1 to ket 0. It's a constant function. And this would be the matrix representation of the function f. Okay. Now, recall that quantum systems, in quantum systems, we require all our functions to be unitary, hence reversible. So we need to make this function reversible. And let's suppose that f is given as a block box, but in terms of its quantum counterparts. Okay, so let's call the quantum counterpart of f UF. Okay, so this is the quantum counterpart of the function f. All right. Now, UF will be given as an oracle, and it will have 2 inputs and 2 outputs. It will be given in the form of a black box like this. It will have 2 inputs, ket x, this is ket y. Well, the first output will be the qubit that we want to evaluate. Okay, so x will be the qubit that we want to evaluate, and y here controls the input. And then in the output we have x, and the second qubit of the output will be y XOR f of x. So, in summary, UF takes the state xy, a 2-qubit state, and it maps to x, y XOR f of x. Okay, so this operator here is simply binary XOR. Okay. All right. So furthermore, if y equals 0, then this expression simplifies to, if y equals 0, then the above expression simplifies to, so xy will be mapped to x 0 XOR f of x. Okay, but this is simply x f of x. Now you can easily notice that UF is reversible. Okay, that is, if we give x y XOR f of x as an input to UF, then the output will be xy. Okay, so let's see that in fact. So if the input to UF is x, y, XOR f of x, okay, so this will output x. I'm applying this function here, so it will be y XOR f of x XOR f of x. Okay, now we know that f of x XOR f of x is simply 0. Y XOR 0 is simply y, so this will be equal to xy. Okay, so let's consider the function. Let's consider the function f defined as follows. F of 0 is 1 and f of 1 is 0. Okay, so it's simply the not function. Now the corresponding UF will be defined by the following matrix. Okay, so if we take this function, then the corresponding UF will be equal to the matrix. So it will map the state 0, 0 to state 0, 1. Right? So the first column of the matrix will be 0, 1, 0, 0. It will map 0, 1 to 0, 0. And the third column will be 0, 0, 1, 0. The fourth column will be 0, 0, 0, 1. So when you give 1, 1 as an input, the output will be, oh, I'm sorry, yes. If we give 1, 1 as an input, the output will be the same. Okay, so now the problem is to determine whether UF is a constant function or a balanced function. Okay, so we're given the function f, given in terms of its quantum counterpart UF, and the problem is to determine whether UF is a constant or a balanced function. Okay. Okay. Now we will use the circuit method to describe our quantum algorithms. There are other methods that we will discuss later on, but for simplicity, we will start with the circuit model, and it's similar to what we did when we generated the EPR pairs. Okay, so now we draw some wires and we used hadamard transform, the C0 gate, and we're going to use a similar approach here. Now, our first attempt, rather than evaluating f on different inputs, so rather than evaluating f twice, let's actually put the input states into superposition. Okay, so this would be the most natural approach in a quantum algorithm. So as our first attempt, okay, first attempt. And now I'm going to give you the wrong solution, by the way, okay? I'm going to give 2 wrong solutions and 1 correct solution in the end. All right, so we try to put the inputs into a superposition. All right, so instead of having the top input to be either in state 0 or 1, we put the top input state in this plus phase superposition state. Okay. So we put the top qubit of UF in state ket 0 plus ket 1 divided by 2, square root 2. Okay, so we start with the input ket 0 and we apply the hadamard transform to ket 0 and then obtain this superposition state, right? So because hadamard 0 is equal to 1 over square root 2 0 plus 1 over square root 2 1. Okay, which is equal to this vector. All right, so let's draw the circuit diagram. We start with the top input will be set to 0, and then we have a hadamard transform here. Okay, so this will be the first input of UF, and we basically set the second input to ket 0. Okay, and then we have 2 qubit outputs. And then in fact, let's measure the first qubit here. I'm going to use this notation for to denote measuring. Okay. All right, so let's divide this into stages. Suppose that this stage is denoted by phi 1. Or let's call it phi 0. Okay, it's phi 0 in the notes. Let's call this stage phi 1, and let's call the final stage, the output of UF, 2 qubit output, let's call this phi 2. Now let's look at each state and how they're defined. Okay, so it's easy to see that phi 0 is simply 0, 0. Okay, the first qubit is on state 0 and the second qubit is in the same state. So this is straightforward. Phi 1 is when the first qubit is put into superposition. So the first qubit is in state plus 0, 0 plus ket 1 divided by square root 2, tensor ket 0. Okay. Now this is the first qubit in a superposition, right? And this is the state of the second qubit, which is unchanged. If we distribute it, we get 0, 0 plus 1, 0 divided by square root 2. All right. Now it's time to apply the function UF on phi 1. Now, UF is a linear function. So, okay, so phi 2 will be actually, so we have UF 0, 0 plus UF 1, 0. Okay. But then we have, as an output, we have 0, F0. Okay, if we apply UF to the first component. And in the second component, we have 1, F of 1 divided by, we have the 1 over square root 2 amplitudes. Now let's suppose that our function was defined as earlier. Suppose that f of 0 is one and f of 1 is 0. Let's think about the worst case scenario, okay? Because we want to have a general solution. Okay, if f was defined in that way, then the state phi 2 would be, so I'm rewriting phi 2, it will be basically 0, 1 plus 1, 0 divided by square root 2. Okay. Now what do we get out of this? If we measure phi 2, the first qubit will be in state, either will be in state 0 or 1. Each with probability 1 over 2 actually. Right? So we get nothing. We have no information about whether the function is constant or balanced. And similarly for the second qubit, there's an equal chance of the second qubit being in state 0 or 1. So now we should devise a better algorithm. So the first attempt fails. Okay, we have no information about the function f. As our second attempt, okay, rather than leaving the second qubit in state 0, let's put both qubits in a superposition state, except that, oh, actually we leave the first qubit arbitrary, but we put the second qubit of UF into the minus phase superposition state. Okay, so leave the first qubit arbitrary and put the second qubit into the minus phase superposition state, that is ket 0 minus ket 1 divided by square root 2. Okay, so let's draw the diagram. We have UF, the first qubit will be arbitrary, so let's call it x. The second qubit will start with ket 1, and then we apply a hadamard transform, because H1 will be equal to the minus phase superposition state. And then we have output wires, and let's again measure the first qubit. Okay, so let's call this state phi 0, and let's call the next one phi 1. Let's call this phi 2. Okay, so it's immediately clear that phi 0 is basically x1. Right? The first qubit is in an arbitrary state that we don't know, and the second qubit will be in state 1. So we start with phi 0. Phi 1 will be the first qubit changed, it remains the same, tensor. The second qubit will be in the minus superposition state, ket 0 minus ket 1 divided by square root 2. If we distribute this, we get x0 minus x1 divided by square root 2. Okay, so now we apply UF to the state. Again, by linearity, phi 2 will be equal to, all right, so let's take a look at the first component here. If we apply UF here, okay, that means the first input to UF is x, the second input to UF is 0. Well, this will be, the output will be x, 0 XOR f of x, right? And then we do the same thing to here, and this will be equal to x 1 XOR f of x. And then we have the common factor, 1 over square root 2. Okay. So this will be actually equal to, let's take out x. X will be our first qubit, and the second qubit will be in a superposition, f of x minus the complement of f(x), right? complement divided by square root 2. Okay, because these will be complement of each other, right? These two components. Okay, so depending on the value of f of x, phi 2 will be in one of the two states. So let's draw an array. Okay, so if f of x is equal to 0, then phi 2 will be equal to cat x tensor 0 minus 1 square root of 2. But if f of x is equal to 1, then we have the same superposition state, the same 2-qubit superposition state, except that we have 1 minus 0 square root 2. Okay? Now, by simple algebra, we know that a minus 1 can be written as minus 1 times b minus a. Okay, if we look at the second qubit of phi 2, they're actually a minus 1 multiplicand of each other. Okay, so we may rewrite phi 2 as minus 1 over f of x as a factor, and then we have x tensor 0 minus 1 over square root of x. Okay, so if f of x is 0, okay, then this will be plus 1, and then we have x, this superposition. But if f of x is 1, then we have a minus 1 factor, minus 1 amplitude, and then the order will be changed in the second qubit. All right, so what happens if we measure either the first qubit or the second qubit? Okay, now if we measure the first qubit, it's in an arbitrary state, right? It could either be 0 or 1. So we have no information about the first qubit. And if we measure the second qubit, well, again, it doesn't give us any information, right? It could be in either one of the superposition state with the same probability. Okay. Okay, so the second attempt also fails because it gives us no information about the characteristic of the function f. All right, so finally I'm going to give the solution. So now the solution. All right. So first note that when the second input to the oracle UF is the minus state superposition, okay, then in fact the output of UF shows a kind of kickback characteristic here. Okay, so we have so this vector is actually the eigenvector of UF. The eigenvector of UF. Because if the input is x and y is equal to this negative phase superposition state, then the output will be the same except that it picks up a phase of -1. Okay. Now we will use this property in the solution. Okay, so let's put first and second qubits into superposition. We put the first and second qubits into superposition. But not only that, but we will also put the output into superposition. That is, we will also have a hadamard transform in the first qubit of the output wire of UF. And the quantum circuit will be defined as follows. We will start with 0. We will put a hadamard transform here. Okay. And this will be our oracle UF. And then the second qubit, we will start with 1. We put a hadamard transform. This will be the second qubit. And in the output, we put another hadamard transform in the first qubit of the output. And then we make a measurement. So we only need to measure the first qubit. That will be sufficient. All right. So let's denote the states. Let's call this phi 0. Let's call this phi 1. Let's call this stage phi 2. Let's call this phi 3. All right, so let's now examine these states. Let's write them explicitly. So obviously phi 0 is equal to state 0, 1, right? And we apply the hadamard transform on both qubits. Well, that means that both qubits will go into superposition. So 0 will be transformed into 0 plus 1 divided by square root 2. Okay. So this is simply hadamard 0. And then we have, in the second qubit, we have the negative phase superposition, hadamard 1. All right. So in fact, this will be equal to, if we distribute it, 0, 0 minus 0, 1 plus 1, 0 minus 1, 1 divided by square root 2, okay? All right. Now, we saw earlier, I just said a minute ago that when the input of UF, when the second input is the negative phase superposition state, then the output will be simply minus 1 over f of x, right? We have this phase. So we have the same situation here. The second qubit of phi 1 is the negative phase superposition, right? So this is actually the input, the second input of UF. So then, so let's write this as a note. So in fact, 0 minus ket 1 over square root 2 is the eigenvector of UF with eigenvalue minus 1 over f of x. Okay, but now we have x in the superposition, right? Let's rewrite phi 2. So phi 2 will be equal to okay, so x is in the superposition state, and then we have minus 1 over f of 0, ket 0. So we write 1 for ket 0 and 1 for ket 1. Okay. Plus minus 1 f of 1 ket 1 divided by square root 2. So this will be the first qubit of phi 2. Second qubit will remain the same. It's still the superposition, the minus state superposition, 0 minus 1 divided by square root 2. All right. So let's now take a look at the numerator of the first qubit. Okay, this part. Okay, so let's look at this expression, and I'm ignoring the factor 1 over square root 2. Now, if f is constant, then the above expression then this either becomes plus 1 times 0 plus ket 1, or it becomes minus 1 ket 0 plus ket 1, right? So depending on how f is defined, but if f is constant, it's going to be, this expression will be equal to one of them. But if f is balanced, well, then it becomes either plus 1, 0 minus 1, or it becomes minus 1 times ket 0 minus ket 1. Okay, so if f is balanced, we actually have the same state except the phase. And if f is constant, we have another state with possibly different phases. So let's sum this up. To sum up, we have that so phi 2 will be either plus minus 1 times ket 0 plus ket 1 divided by square root 2. This is our first qubit, and second qubit will be 0 minus ket 1 divided by square root 2 if f is constant. Okay, if f is balanced, then we have plus minus 1 times 0 minus 1 divided by square root 2. Second qubit will be the same. And this is when if f is balanced. All right. So phi2 will be either one of the, it will be in one of the states depending on whether f is constant or balanced. Okay. All right, so here comes the trick. Now the trick is to apply a hadamard transform on the output of the first qubit of UF. So we're here now. Okay, phi2. And depending on whether f is constant or balanced, it's in either one of the two states. And we're going to apply a hadamard transform on the first qubit. Okay, on the first qubit of phi2. So what's going to happen is that hadamard transform is its own inverse. Okay. That is, if we apply hadamard 1, if we apply a hadamard transform on hadamard 1, we get 1. And similarly, if we apply the hadamard transform on h0, we get 0. Now, so this is what? This is actually hadamard 0. But if we apply hadamard 0, if we apply the hadamard gate, the hadamard transform here, on this superposition state, well, we get 0. Right? So let's write phi 3. So phi 3 will be, it's either going to be plus minus 1 times ket 0, 0 minus 1 divided by 0. This is if f is constant. Okay. And then if f is balanced, if we are in this superposition state, and if we apply the hadamard transform on the first qubit of phi 2, so this is already hadamard 1. And if we apply the hadamard transform on this superposition, we have ket 1 times ket 0 minus ket 1 divided by square root 2. And this is when f is balanced. So as soon as we apply the hadamard transform on the first qubit of the output of UF, we get an interference, right? The interference phenomena. Okay, so if we measure the first qubit then, if we measure the first qubit of phi 3, what we see is that we see ket 0 with probability 1 if f is constant, right? But if we observe ket 1 as the outcome of the measurements, then we know for certain that f is balanced, right? So we in fact did this with just one evaluation, and this is why in this problem quantum algorithm outperforms the classical algorithm. While classical algorithm requires 2 queries, quantum algorithm required only 1 query. So with only 1 query, we know for certain whether a function is, any given function f, a binary function, is constant or balanced. Okay, so I'll see you in the next lecture then.